Happy to go ahead and get started. So welcome everybody. Today I'm really excited to introduce Professor Cara Nunez, who will be giving the Ezra seminar today. She's an assistant professor in the Sibley School of Mechanical and Aerospace Engineering since July 2023. Prior to this, she was a Cornell Provost Faculty Fellow and conducted her fellowship at the Harvard John A. Paulson School of Engineering and Applied Sciences as a member of the Biorobotics Laboratory, the Microrobotics Laboratory, and the MOVE Lab. She received a PhD in bioengineering and a master's in mechanical engineering from Stanford, working in the collaborative haptics and robotics in medicine lab in 2021 and 2018 respectively. She was also a visiting researcher in the Haptic Intelligence Department at the Max Planck Institute for Intelligent Systems in 2019 to 2020. She's received her bachelor's in biomedical engineering as well as a second bachelor's in Spanish as part of the International Engineering Program from the University of Rhode Island in 2016. She was a recipient of the National Science Foundation Graduate Research Fellowship, the Deutscher Akademischer Austauschdienst.
A German fellowship.
Yeah.
Deutscher Akademischer Austauschdienst. Yeah.
Perfect. Graduate Research Fellowship, the Stanford Centennial Teaching Assistant Award, and the Stanford Community Impact Award. Her work has been a finalist for the Best Technical Paper in the IEEE Haptics Symposium in 2020 and 2024, and her research interests include robotics, haptics, and human-centered design for medical applications, human-machine interaction, augmented and virtual reality, and STEM education, among others. So please join me in welcoming Professor Nunez today.
Great. Well, I'm really excited to be here next door from where my lab and office are over in Upson. So if anyone's ever curious and wants to come check out some of the things that I'm talking about in my talk today, or just wants to get sort of a tour of the lab, we're very friendly people. We'd love to have you stop by. So feel free to come up at the end of the talk if you'd like to chat a bit more about that. So thanks, Maha, for the wonderful introduction. If it wasn't clear from the very long bio, I work in the field of haptics. And that's really what my talk is about today. Specifically, how do we actually design, control, build these systems, these haptic systems, and really bring humans in the loop in that process so that we have these really well-functioning devices in everyday life. So I like to call this engineering touch. So we're really building these systems in engineering touch. My lab, we have a wonderful name. We are the Happy Lab, full of happy people. Although we work on haptic systems, more broadly, we work on technology that augments human performance, both in physical and perceptual environments. So again, thinking about out in the real world in reality or in virtual and augmented reality. Again, happy to introduce you to my lab and my lab members at any point on campus. So with that, I'll sort of start by just saying, I'll go to the next slide here. What is haptics anyway, right? Probably this buzzword that you've heard a lot lately in recent times, or maybe you have a smartphone in your pocket that has a haptic setting. So haptics is actually a very, very old field that was defined by the Greeks back in 1890, and it's really of or related to the sense of touch, so anything connected with the sense of touch. And it kind of has these roots that are connected with grasp and touch itself. And so, again, this is more than just the vibration of the phones in your pockets. Really, our haptic senses work together with our motor control system to help coordinate movement and enable our perception. So think of this sort of example here. Touch is really, really important. If you have, for example, a pitcher on a table and a glass in front of you, you want to be able to reach out and pick up this pitcher, pour it into the glass. You want to know if this is water or if this is cold water or if this is a hot beverage. And the way that we do that is coupled, again, with our motor system, so being able to actually move out and pick up and perform these muscle-based tasks, but also understanding the contact forces to be able to adjust that movement. And so actually this can be broken into sort of two elements of haptics. One is kinesthetic haptics. So these are things that are embedded in your joints and in your muscles. to help you understand, again, those sort of movement-based actions. So again, reaching out, understanding where your hand is in space in order to be able to pick up that picture, the motions themselves, how quickly are you going or not going, the forces, so how heavy is that picture. Compliance can again be that handle that you're picking up, is this metal or is this something that's maybe a little softer, like a silicone, so that when you're grabbing it, it's not totally buckling in your hand. But then we also have another part of haptics, which is your cutaneous sense of touch, also called your tactile sense of touch. And instead of these being embedded in the larger parts of your body, so thinking about your joints and muscles, this is actually your sense of touch embedded directly in your skin. So there are a bunch of mechanoreceptors embedded in the skin that give you these tactile information. So you can think when your skin contacts this glass in front of you here, you could tell, again, the temperature of the liquid that's being poured in. Is this water? Is this hot coffee? You can get textures. Again, is this a glass sort of cup, or is this maybe ceramic? You could feel a little bit of the difference in the grooves of the cup. Slip, you could see, is this slipping in your hand as you're pouring that liquid in? Vibrations, again, you can think these big picture vibrations like your phone, but you could also think maybe the micro vibrations of water being poured into that glass. You can actually detect that. And then again, there's sort of this commonality here of force, but it's force maybe at a smaller scale pertaining to, maybe changes in your finger pad. So being able to kind of connect all that together. So again, we can kind of break haptics into sort of these two categories. There are lots of different projects and research questions and things that connect with both of these elements of haptics. But I'm really going to focus on this cutaneous part of haptics in my talk today. So really how we can manipulate and understand mechanoreceptors in the skin to create devices that can create these really cool sensations. But again, haptics is actually a really big field. So to kind of motivate why we even care about haptics and touch more so again than maybe these vibrations of your smartphone, right, is what would life be like without touch? So especially looking at what life would be like without touch of this cutaneous or tactile type of touch. So there's this really great study done in Sweden back, I believe in the 80s. Let's see if this video will play here, where the researchers said, okay, we're gonna have you perform this really simple task. Reach out in front of you and pick up and strike a match. And you can see this video actually ran so quickly that it happened right away. It took about 2 seconds, right? They reached out, easy, they could see the match, they could feel it, they picked it up, they could find the box, struck it, we're done. And they said, okay, now what we're gonna do, this goes, is we're going to anesthetize the participants' fingers. So we're going to take a needle. I'm not going to show this part in case people are a little squeamish. But they take a needle and they insert it and they anesthetize specifically the mechanoreceptors in their finger. So again, these are the same mechanoreceptors that I was talking about before that help us understand about the pitcher and the glass and understanding these different properties of the interactions. And so these mechanoreceptors basically fall asleep because they're anesthetized. But everything else with the participant is fully functioning. So they have full vision, they have full motor control, right? So nothing changes in the motor system. They're able to actually perform all of the tasks normal. The only thing that they don't have are these sensors in the skin. And basically what we have here, if this video starts to play, which it will, same exact task. They say reach out, try to pick up this match, and they really, really struggle to do it. So again, they can see everything, they can move as normal, they just aren't getting the tactile feedback to actually pick up and move this here. And eventually, they do complete the task. It took me about 1,000 views of this video before I realized that they cheated. It's the only reason that they could actually go and pick up this match. So they only anesthetized the thumb and the pointer finger. So all of the attempts to pick it up, they were initially using the pointer finger and the thumb, which is how they did it the first time around. When they were struggling, they went and they used their middle finger. And they went and they picked it up because they actually had full functionality in that finger there. So like I said, I've seen this video a ton of times, and it took me a really long time before I realized that. And actually, in order to be able to perform the task at all, they had to cheat and use something that wasn't anesthetized. So to me, when I first saw this, it was really, really eye-opening. I didn't realize how much I really needed the sense of touch. Again, this is pretty abstract, right? So most people are not going to go around and anesthetize their fingers. But a way that you could think about this a little bit, it's easy to relate to here in Ithaca, especially 2 weeks ago when it was really, really cold. Think about when your hands freeze, because it's so cold outside, you don't have your gloves, your mittens on, and you're trying to zip up your coat. It's the same basic thing here, is that our mechanoreceptors aren't really able to give us that feedback that we need, and so the tasks become a lot more difficult. So imagine if you had to deal with that all the time. And part of why I like to bring this up is if we think of robotic systems, most of them don't have the same level of tactile sensing. So these complex mechatronic and robotic systems aren't able to do the same level of performance that we have because we're kind of missing this ability here. Again, maybe a little bit difficult for people to imagine or envision. So another example that I sort of like to think about here is what life would be like without touch. Unfortunately, we all can relate to life without touch during COVID, where we had to be isolated 6 feet apart. And so during this time, as you guys definitely experienced as well, we were able to transition to having some things be fully remote, right? Like we had fully remote classes, workplaces, general other environments. But unfortunately, those were really only through touch screens, mice, over the phone. We became really dependent on these technologies, spent a lot of time with it, and it's successful to some extent, right? But what we also tend to notice is that there's an emotional disconnect and overall usage of all these technologies is very stimulating, and we end up getting really fatigued. There was this wonderful term that was coined during this period called Zoom fatigue, which is basically saying there's a limited amount of time that you can really be on this technology before you're totally drained. And so part of why this is that, again, these methods are not the ways that we typically interact with the world, right? Like we typically interact physically. We basically are not taking into account our normal physical and emotional channels, and we're focusing primarily on visual and audio feedback. So we're kind of removing that tactile feedback, which is giving us a lot more information than we realize and taking some of the load off of these other channels. So, sorry, Gary. My general research goal is how can we actually incorporate novel haptic systems into these type of interactions. So it could be things, connected with Zoom, but it could also be bigger picture than that. Really any forms of advanced technology. So I've got here some examples showing sort of human-human type of interaction. So again, imagine that in addition to having the video and audio that you might have on a call, you'd also have some haptic systems giving you additional information. It could also be interactions between humans and machines. So thinking here, like if you're driving in your car, being able to get information haptically instead of having to look down at now these really large screens that are existing in new cars. But it could also be with robotic systems in the home or other general machine systems. So, a very common technology now in people's homes are Roombas, but these kind of go around and they operate autonomously, but it'd be really great if you weren't running into them or they weren't kind of constantly cycling through areas that they've already been through. So could we communicate with these type of technologies through intelligent haptic means? And again, while I kind of highlight a couple here with some different schematics, there's so many more ways that we can sort of incorporate haptics into different tasks. So there's also opportunity within search and rescue, teleoperated robotic surgery, so going away from sort of manual surgeon-based surgery to using robotic systems. Other assistive devices, you could think prosthetics or exoskeletons. And then a big one too is sort of collaboration with industrial robots or other large robot settings, or even robots, like caregiving robots in the homes. There's so many different ways that haptics could play a role connected with these intelligent systems. And my goal is to try to work to create these effectively, both from the hardware and control side, but then also making sure that we're taking into account the human side. Okay. So with that, as you can imagine, there's a lot of challenges. Why I think this field is really exciting is that these challenges actually really lead to opportunities. So my work kind of works in these three areas to overcome these challenges. So specifically looking at the system design, so looking at building the hardware, both sensors and actuators, also building control schemes that work with those sensors and actuators in the overarching system. and having that connect really well with understanding human haptic perception, so specifically kind of the biology of it, and what, you know, the cognitive loads and things like that. But then also trying to connect that with very specific human machine or human robot interaction scenarios. And so I'll kind of talk about some of the challenges in each of these areas, and then throughout my talk you'll sort of see how we look to address some of those challenges, but also where there's areas to move forward. So for system design, so again, my work has really focused on these wearable, tactile, haptic systems, so things that are focusing on the skin. And pretty much if you want something to be wearable, you want it to be a couple different things. Small, lightweight, low form factor, right? Like you don't want to wear this big bulky thing to give you just a little bit of information. We want it to be really compact and discreet. And one of the big challenges with that are actually the actuators that you use. So if any of you are maybe a little bit more on the ME side of systems engineering, you'd probably identify this as a common rotary motor. So that would just do sort of rotation-based motion. You could attach an end effector to it to create different types of stimuli. Then we have a bunch of different types of smaller vibration-based motors. One is an eccentric rotating mass motor. So that's the first one there, which basically is an uneven distribution that rotates and creates a vibration. We also have things that are a little bit more compact, like a C2 tactor, or voice coils, that can also create vibration. They can also be manipulated to create different types of stimuli, which I'll talk about a little bit more in my talk. But overall, these are kind of like the smallest actuators that you can really find off the shelf. In addition to the size and the weight, there's sort of constraints on the frequency or the force output that each of these could give, right? So you're trying to balance all of these different components together. And oftentimes, we're not quite able to get the range that we want or that matches sort of human levels of perception. So there's been a lot of work in developing new novel actuators. So some of them are piezo-based actuators. There's fewer of these on the market, but these are starting to exist more and more. But then something that I've been really interested in and has been pretty novel in the last 5-10 years or so are using soft actuators and techniques to build different types of soft systems. So some of them are using pneumatics. So this here uses a very low-cost LDPE plastic, so think like a Ziploc bag. And you basically can take it and heat seal it into different shapes to create different profiles that you might be able to create actuation just by having fluid flow in and out. There's also work with polymers and elastomers, but these are all very, very new and ongoing, not something that you could just go and buy off the shelf. So again, with any of these sort of actuators and things that you're designing, as any engineer always knows, there's trade-offs, right? So as I mentioned before, kind of looking at some of these different actuators, we can see, we might have more ability to customize, or we have a wider frequency range, but maybe what that's going to do is add weight or cost to the actuator as well. So we're constantly sort of balancing this trade-off. But ultimately, we kind of want to be in this general range here, where we have a low weight, we want a low weight but a high power ratio. So we want to make sure that we have high output or high range with a low weight. And in general, you can see from these boxes here, that area is not particularly well explored yet, or there aren't successful actuators and systems yet. There are some work, again, the example that's sort of here are these shape memory metals. So these are things that we're able to get a large output on. But one thing that's really important for haptics is frequency. So these shape memory metals, basically, they can change from one state to another really fast, but it takes a really, really long time for them to go back to their initial state. So maybe it's kind of a good thing for general robotic systems or other systems, but it's not actually all that great for haptics. So I put a little caveat here that while we technically have some actuators that fit in this part of the graph, they still actually don't quite work for haptic systems. So we're really trying to move towards developing things in that area. Okay, so some other challenges. So that was mostly on the hardware side. Now we still have challenges, which is on the human side. So we have a really, really good amount of knowledge of human haptic perception at the fingertips and hands, which makes a lot of sense because when we think about how we interact with the world, we're often picking things up or grabbing things or contacting in that way. But we also have haptic perception everywhere else in the body. Anywhere where we have skin, we have the ability to perceive interactions, right? But we just haven't quite gotten to a full understanding of the capabilities of all these different areas. So here in the skin, we've got a nice cross section pulling out these mechanoreceptors. And we can see that there are different mechanoreceptors that respond to these different types of stimuli. So I can mention slip, vibration, force, all these different things. They're very well mapped to the hand, both the density and the general number of them, so we know how many there are and kind of where they're placed and where they're the most dense. And so for example here, these are the Pacinian corpuscles. We can see that there's a lot of them, especially at our fingertips, and these respond to vibration. So this is very common that we're using different types of vibro-tactile stimuli. So like I said, we know a lot of information about the fingertip and the hand, but what about the rest of the body? There's been this really big shift recently to trying to understand more about these other areas of the body, but we're just quite a bit behind. And a big reason why people are starting to care about these other areas of the body is if we're going to be developing these technologies, right, that are going to give us this additional information, we don't really want to design them such that they're in contact with your fingers or hands. Because, say I want to go and pick up and drink a glass of water while I'm on a Zoom call with one of you guys, now I've got some bulky thing on my hand that's not going to let me open the top here and get a glass of water. So we want to try to move away from actually building systems on the fingers and hands, so we leave those open for your everyday tasks. So we're able to give you information elsewhere. All right, so then sort of the last challenge / opportunity that I'm going to talk about here is actually the challenge in understanding this human-machine interaction. So the scenario that I'm really going to talk about in my talk today is really pertaining to social touch. And so social touch, as you might imagine, is a really critical aspect of interpersonal communication. So the examples I have here are like a friendly introduction to a colleague. You normally reach out and shake their hand. If you want to express love to a family member, you're often going to give them a hug. Or if you're going to comfort a friend, it's really common to kind of put your hand on their back or on their arm and sort of softly and gently touch or stroke them. So these are really, really common ways that social touch is used in everyday life. But it's really, really difficult to build systems that replicate these types of touches. One, because as you could probably think, when your friend's comforting you, reach out and comforting you, it doesn't feel anything like your smartphone, buzzing with an alert, right? It's a totally different type of sensation. So we have to figure out what the different elements are that are involved in these type of touches and try to relay them such that it feels realistic, as opposed to creating what's called an uncanny valley, something that's maybe close to the type of sensation that you're trying to relay, but it's not close enough, so it becomes awkward and weird. A really common example of an uncanny valley is the Polar Express. Have you guys seen the Polar Express movie? So that was one of kind of the first examples defining an uncanny valley because, movies, they were going towards making things really realistic. And so they tried to make it realistic and it ended up being a little bit weird. So that's kind of a common example that people are using when they talk about, photos and videos. You can imagine maybe there's something similar with haptics, right? That you might reach something where it feels kind of close to human touch, but it's not quite there, so instead it just feels creepy and weird. So we're trying to avoid that and instead have things that feel realistic. So again, this is really challenging to do. Okay, so now we get to the meat of the different things that we have done working on some of these challenges. So I'm going to talk about sort of the design and modeling and control of a couple different systems for the forearm. Then I'm going to talk about actually understanding the perception of these cues that we're able to create on the forearm. So again, these are for specific social touch interactions. And then I'm going to talk about a different system that's much larger that leaves the forearm but goes to this larger area of the dorsum or the human back. Okay, so we'll start with designing the design of these systems on the forearm. So I'll specifically start by saying that we're really looking at a stroke on the forearm, just like what's in this video here, something that is slow, gentle, kind of moves laterally. You might say, okay, I see this, I could build this system that I've got one thing that's on a linear actuator and it's just going to slide. I could build this really complicated thing. But we said, okay, the more complicated you're gonna make it, the harder it is it's gonna make it be wearable, right? So let's try to break down this type of touch into discrete components and see if we can use some really small pieces to actually create this lateral continuous movement. So we're calling these haptic illusions. So there's a bunch of different examples of haptic illusions over the years, but this is basically saying, can we trick the person into thinking that it feels exactly like this nice, smooth, stroking touch, when in reality, maybe it's discrete components that are from mechanical or an electrical means, not from a human hand. So what we did is we started with these really low cost, we call them haptic sketches. So this is just taking really cheap items that are around the lab. So I used a lot of hot glue, Velcro, magnets you can see here, some 3D printed things. But in general, it was just really cheap things that we could basically prototype really quickly to see what could actually create this sensation. So here are basically the two most promising ones. So one was to say, let's just take an array of magnets, and then we'll take another magnet and basically just slowly move it over that array and have these magnets propel into the skin. So you could basically do it with a single magnet, or you could do it with multiple magnets just to create a stronger force. And ultimately here we can sort of very lightly model what that motion is. But we're actually able to create this nice press into the skin with these magnets. A second sort of sketch we made, and this is one of the more complicated ones here, was basically saying, oh, I can have these discrete rollers, or these things that when I pull along a linear slider here with some grooves, I can get these to turn, and now I've got things that are kind of discretely rotating along the arm. So we piloted these along with a bunch of others. We brought in some novice people that are not involved in the design process at all, and just had them feel these, and they were like, oh, this feels really nice and pleasant, which again is not words that are typically used for haptic or robotic systems. So we said, okay, this is obviously just the sketching part, let's actually build it. Sorry, I actually talked about this in detail already. So here's our electromechanical system mimicking this magnet array. So I mentioned earlier voice coils as an actuator. We use these voice coil actuators. This is a slightly different design than the one that I showed here, but these could also be thought of as mini speakers. And so basically you can design a signal, send it through, and then it's going to move based on that signal that you sent in. So you could send it and have it vibrate. We actually created custom signals such that we could control the motion more directly. But we put them in this linear array, just like you saw with the magnets. But the beauty of this is that we don't need that second external magnet to kind of move over it. We can actually just directly control these actuators with the signals that we're providing there. So you can see it's pretty lightweight, it's pretty compact. It's not quite as tight as my jacket up here, but it's pretty good form factor. I'm sure that over time we could make it lighter, smaller. But in general, this was sort of the first prototype here. As we then went to look at how could we actually control these actuators to move as we wanted it to. So here, like I mentioned, we could send a signal that would just oscillate and create a vibration. But instead, we created a custom signal that basically said, when the device is worn on somebody's forearm, the tactor, or that voice coil, is always in contact with the skin. So we want it to lift up off the skin. So we're going to actually have a signal that retracts it away from the skin. Then we're going to use a nice smooth quadratic profile to have it slowly indent into the skin, just like sort of what we were seeing with our magnet array. And that same profile is then going to have it move back away from the skin. So we created, again, it kind of looks like a sinusoid. It's not quite a sinusoid, so it's pretty similar still to maybe a traditional vibration, but really it's slightly customized, and it's an individual sort of signal that we're sending to each voice coil. So what we do then is say, okay, if I have this signal, I can send them to each of my actuators in this array, and I can control how much time between the signal that I send for each of them. So what's the delay between when I send the signal to the first actuator versus the second, etc. And so here you can see with a very small delay, 12.5%, this sort of bottom plate here is a heat map showing the amount of overlap between these actuators. So if it is a dark red, that means basically multiple of them are in contact with the skin at the same time. Versus if I have a larger delay, you can see that this is pulled out quite a bit. Maybe there's a little bit less overlap on the skin. We looked at this and said, our hypothesis is the shorter that time period in between, so sort of this 12% delay here, it's probably going to feel smoother, more continuous, because we've got multiple that are in contact with the skin kind of at the same time, versus if we keep increasing this delay, or there's probably at some point where it no longer feels continuous and smooth, it's going to feel like individual pokes on my arm, right? So we were looking to see kind of how does that come into play. So here, again, this is a video showing you of what this would look like if it was contacting into your arm. You can see each one is actuating individually. It's moving basically just normal. It doesn't really look like a traditional vibration because it's not. But you can see that it's controlled sequentially to press into the user's arm. And then what we did is we conducted a user study to basically try to understand how does this feel on the lower and upper arm, so these areas where we do typically have this type of social contact. How does changing the pulse width, so the total amount of time that this signal actually occurs, you can kind of think of this as the speed, although it's not quite the speed. So a shorter pulse is something that's going to happen really quickly, something like that, versus a longer pulse is something that's going to be a little bit slower and maybe smoother. And then again, looking at these different delays that I mentioned, so the time in between each actuator. And then one thing we wanted to try as well was if we would overlay a small amount of vibration on that signal. Maybe you can kind of think of it as micro vibrations that might be occurring from, for example, touching the hairs on the skin as you're moving along the skin, or not adding if there was sort of a difference there. So within these studies, and what's pretty typical within haptic studies is that you obviously build a system and you collect data, but you also get a lot of user responses. So we conducted studies asking them to rate things on Likert scales. So here you can see these Likert scales where they give a rating for how discrete or continuous it is, and also how pleasant or unpleasant it is. And this is in addition to sort of these open responses at the end where they can just give us general feedback. So what we ultimately found, I won't show you all the plots because I find it's easier to just look at the videos here, is that slow pulses with long delays feel discrete. So you can think about these pulses that are really long, it's kind of moving really slowly, and there's a lot of space in between them, feel discrete. So you could think of it as like, oh, I've got maybe my actuators on my arm, it's like 1, 2, 3, right? That doesn't really feel like this nice smooth motion. Versus really fast pulses, so things that are these really short pulses with short delays, so the complete opposite end of the spectrum. Although it maybe feels slightly continuous, it feels really unpleasant. It's like kind of like a type of feeling as opposed to something that's more calming, comforting, gentle. So what's the most continuous and pleasant is sort of a combination of these two things. So we've got our long pulses, so these things that are a little bit slower, but actually have these short delays between them. So again, if we think back to our heat map there, we've got things that are very much sort of on top of each other, but the overarching piece itself is actually a little bit slower or longer. And what's really exciting about our finding here is that we can actually calculate what the speed of motion is along the arm. So we can take this pulse and we can take the delay and say from the time the first contact is made from one actuator to when the last actuator leaves my skin, I know the distance that it traveled and I know the speed that it, like the amount of time that it took to do that, so I can calculate the speed. And ultimately what these speeds are between 5 and 10 centimeters per second, which is something that was found actually while we were doing this study in biological research, that there is a mechanoreceptor specifically embedded in hairy skin, so hairy skin like what's on the forearm versus glabrous skin, which is what's on the hand, so things without hair, called the CT afferents. Which selectively respond, they say, to 1 to 10 centimeters per second. So we're right there in that window with what these biologists have recently found as afferents that exist, mechanoreceptors that exist in the skin. So we were really excited because for us, we're trying to design these systems and see what works, but when we actually have grounding in biology, it's really great as well. So we were super excited about this. But we kind of had this follow-up question of what happens if we combine sort of direct lateral motion with illusory lateral motion. So think of the illusion of this voice coil or this magnet system where there's no lateral motion whatsoever. It's all normal indentation into the skin. The only lateral motion that's existing is simply from the fact that there's an array. Versus direct lateral motion, so thinking of kind of our second system that we prototyped there, that we have this lateral motion from these roller pieces that are kind of slipping along the skin. And so we are sort of calling this discrete lateral skin slip, and basically saying, does this improve the continuity or not? So again, we're looking back at this other haptic sketch and trying to see what kind of impact it makes. So same thing, I will comment, this is clearly not nearly as nice of a form factor as our other system. It is not easily wearable, but we were mostly looking to understand the mechanism and figured we could implement other ways to make it more wearable later. So what we have here is we're taking our linear rotary actuators, we're attaching end effectors to them, and basically we are having these then rotate sequentially in a similar manner like we have with our voice coil actuators. But now our controller is not quite as interesting looking because again, we just sort of set it to a speed and it makes contact, but we can control that delay. So we sort of have the same thing and the same general type of hypothesis that the shorter the delay here, the more skin contact overlap versus the longer delay. You can really see here, it's really pulled apart to be discrete. Unlike our previous system, which is pretty easy to calculate the apparent speed, this one's a little bit more complicated because we have to calculate the amount of time that the actuator is actually in contact with the skin. So I won't go through in depth the math here. If you're interested, you can see the paper. But basically, we modeled this, pulled out the different equations for the actuator, the contact with the skin, found kind of the local velocity of an individual tactor. But really, the key takeaway is that our apparent velocity is not actually the same, and we have to take into account the number of actuators that are there. But basically, we can still pull out and calculate this apparent speed. Again, this is important because we want to try to validate if this still connects with this CT afferents mechanoreceptor that we just found. So we conduct another user study. Again, we're trying to look at multiple areas on the body. So in this case, instead of looking at the upper and lower arm, we're actually looking at the lower arm, but the top and bottom, so the volar and dorsal part of your forearm. We're looking at different angular velocities. So this is not exactly the same because it's a different actuation mechanism, but it's similar to thinking of the pulse width. So what's that speed that this is moving at? And then also these delays. And ultimately, again, I won't go through everything, but we found again that these speeds of 5 to 10 centimeters per second feel the most continuous and pleasant. So again, we're finding these same speeds that we saw before. There's a common thread. Clearly, if we can design systems that connect with these speeds, we're going to be successful. And it sort of doesn't matter too much what that mechanism is. Okay. The other thing I will say is we conducted an open response paradigm after this. Mostly because we looked and we said, okay, we're doing these studies where we're having them respond with these Likert scales, we're getting these ratings that we can then run statistics on and pull out all of these conclusions, but all we know is it continuous and is it pleasant? We don't actually know, does this feel like human touch? Do they like it? Like, we're just getting these like very specific values. So we conducted another study where we brought people in who had not experienced either of the devices before. We asked them to feel this one here with the sort of rolling skin slip mechanism, and we asked them to just qualitatively describe the sensation. So that was it. We gave them no pretext, no context, nothing. We just said, come in, tell us what this feels like to you. And we were really pleased that they specifically used the words continuous, that it was something that felt continuous. They used words like fun, that they liked it. They said things like it felt nice. And then probably the best part about all of it was there was multiple people who specifically described it as a person reaching out, stroking along my arm from the wrist up to my elbow. They used words like comfort and soft. So to us, it was like, oh, they're describing exactly what we were trying to recreate. So this is my sort of statement that it's important to not only do the quantitative type of rigorous data collection methods, but also to do more qualitative means to find maybe descriptions or things that you wouldn't otherwise be getting just quantitative measures, that both of these are important. Okay. In addition to sort of validating our design, it also gave us some insight as to how people actually think about these different systems. So they tended to give really, really informative responses as well. So you can see here, people are like, oh, I took about 2 fingertips width, again, dragging from the top to the bottom of my forearm and lifting up slowly. You can tell maybe some of the people we tested on were engineers because they used words like friction, different things like that. So, and then, you know, saying things like it felt pretty consistent in force, things sliding. So, you know, again, we really want to try to collect these really descriptive means because it can give us some ideas of what things people are kind of keying in on that we should either improve or maybe emphasize. Okay, so we talked about the design of these devices. That's typically the longer portion here. But now I'm going to talk a little bit more about additional ways that these are perceived and how this connects more with our application area. So we did create these 2 systems. We did evaluate them. They both were successful, but we really kind of cared more about, okay, how can we make this smaller? These are still pretty big. What's the impact of contact spacing? So we have these arrays. Could we basically like bring it closer together to make it a little bit more compact? Or could we pull it apart, maybe leaving room for wires or different things that we want to embed in or other things that we want to incorporate? So how do we actually have to structure this? And so what we did was we said, okay, let's take the same system, let's design a mechanism that we can specifically control the spacing between each actuator. So we just laser cut some pieces here, and basically we would slide it into basically make the contact spacing between the actuators really, really small, or to spread them apart. And we ultimately then ran another follow-up study. And what we found, again, I'll just jump to the conclusion here, is that increasing this spacing had no effect. So we got the same result if these were pushed really, really close together, or if they were pulled as far apart as possible that we could get it to fit on somebody's arm, right? So we could potentially continue to pull these apart, right? But eventually we're gonna be dropping the number that we can have contact the arm because people's arms are only so large, right? So that's pretty cool because again, if you're a designer, if you're somebody who's building a system, we're just looking at one very specific thing that we want to build in, but oftentimes there's many different components or things that you want to add. Having flexibility in this array and how you space things makes it a lot easier. So we were really excited, again, about that finding as well. But it raised some additional questions of, again, you know, how do these actuation methods actually compare to one another? Why would you pick one or the other? They both seemingly work, but, you know, are there reasons why you might pick one or the other? And then also, this is stemming from the idea of we're pulling these apart and we're running out of space on the arm. Could we pull them apart and actually drop the number that we need? Or could we just reduce the total number that we need because then we need less power, right? It's overall less weight. So could we just drop? What's the fewest number of contact points we need actually to have this illusion hold true? So again, we ran another user study because that's what we do in haptics, where we basically took our 2 devices. We brought the new people again in, but they felt both devices this time, where we changed the number of contact points that were actuated. So we didn't actually physically remove the actuators. We just didn't have them do anything. And then we had people rate again on Likert scales, and ultimately what we found was that this motor device, as we slightly expected from our hypothesis of this included lateral motion, was more continuous than the voice coil device, but ultimately the voice coil device was deemed as sort of more pleasant. There's likely a couple different reasons why people liked it better. Could be that overarchingly the form factor is a little bit smaller and more comfortable. Could also be the specific contact area of each of these actuators is slightly different. The voice coil is this nice sort of circular piece versus these tactors are these smaller pieces that kind of in contact and slip. But really excitingly, we found that you actually only need 4 contact points. So you just need 4 individual presses for something to feel like a stroke, which is still kind of blows my mind. Again, anyone is welcome to come try this in the lab at any point in time. And again, we asked them if they had a preference. It's mostly kind of split down the middle. It's pretty 50-50, but there was a little bit that leaned sort of more towards liking the voice coil device than the motor device. So again, this is kind of a cool finding that depending on your other application or your other needs for the systems that you build, you could potentially use either of these devices. So again, if you're designing very complicated systems, it's great to have a little bit of flexibility there. Okay, so we did all of that. We built all these systems. We found that we can create this type of stroking. But what else can we do, right? Like, that's not the only type of social touch. I led in with, oh, there's all these different types of interactions. Can we continue to build on that? So while we were able to just start with a singular one, we said, let's see if we can build on this and try to understand different social touch gestures. But in order to do that, we actually wanted to study more explicitly what these gestures are. So we have kind of general examples of people kind of contact the arm and do this, but what are the forces involved in those touches? How long do they make or break contact? What's the movement like during these type of interactions? So we have this pressure sensing sleeve that we worked with the design company IDEO to build and then sent out to another company, PPS, which is basically a sensing company, to build this sleeve that can be worn on the upper and lower forearm and collect temporal and pressure-based data of different touches. So we conducted a user study where we had pairs of friends or individuals in a relationship with one another come in. We had these scenarios that were created to specifically connect with 6 different emotions, getting somebody's attention, so attention seeking, gratitude, happiness, calming, love, and sadness. You'll notice these are primarily positive emotions. We intentionally did not look at anger, frustration, things that were more negative. And basically what we did was we created these more like social-like scenarios. So I won't describe all of them, but again, they're in the paper. But essentially one partner would have a pair of headphones on that they'd be listening to a prompt that would say something like, you're at a party and you're in the midst of conversation and your partner reaches out to you as they're trying to get your attention. And then the person who's their partner would be hearing audio that says, you're at a party and you're feeling uncomfortable. You want to get your partner's attention so that you can tell them you want to go home. And they're then prompted to basically contact their partner. So that's what we're basically creating, these types of scenarios that are grounded in the real world to try to understand how people would actually communicate in these types of scenarios. So we have this set up. We conduct this study with 20 pairs of participants. And then we take all that data and we're able to say, okay, for each of these different scenarios, we can classify the contact into these different type of gestures. So we've got squeezes and pokes and strokes, some patting, some tapping, and we can basically say for each of these scenarios, we can break it into these different pieces. We can understand the pressures and the forces and the general times where they're contacting and pull all of that data out. And then we said, okay, if we want to create these different types of gestures, clearly we need more than just the stroking. Let's take our 1D array and build a 2D array. So now we've got, we decided to use voice coils in this scenario just because it was cheaper and easier to build. But again, probably could have used our roller prototype here. But we basically said, okay, we'll take our voice coils and we'll make it in a 2x4 array instead of our 1x4 array. So now we have this, we'll say, okay, let's take our pressure sensor sleeve. If we have kind of this contact here, how do we map the contact from the sleeve to our voice coil system to try to do this sort of data-driven social touch gesture? So basically we take all of that data and we do that. And the process here is basically we're taking the raw data from sort of our stage 1 study. We're filtering them, we're doing all these great steps to make them nice and clean. Then we're running things through a neural network to see what's the most common type of touch for the specific scenario. We ultimately then pull out that one scenario, or one instance, one type of touch for each scenario. So we end up with 6 test signals. So we don't have tons of different types of interactions for each scenario. We just have 6, one for each. And then we basically run it through our mapping algorithm to say if this was the data from the sleeve, how does it map to our system? And then finally, we conduct another user study to say, all right, now we have these data-driven signals, how do people actually interpret them? So if we look at this here, this is the result of our study. One of the few times I will show data. This is called a confusion matrix. This is basically saying if somebody is presented with a signal for a particular scenario, so attention, how often did they recognize that that was attention that was relayed to them? And you can see in our human-machine interaction scenario, so this is the data from our study, identifying attention is really, really good. You can think attention as a scenario is maybe a little bit simpler than something like love. Love is pretty complicated, and as you might imagine, then here our ability to identify love is much lower than our ability to identify attention. So if our system was perfect, then along this diagonal here, this would all be black, and it would be 100%. And you can see there's some things that love is often confused with calming, sometimes a little bit of happiness, and as you can imagine, because some of these things are actually kind of connected with each other. Often, if you're trying to express love, you're also trying to express that you're happy or that you're trying to be calm. So this is sort of our data here, using our devices to replicate human touch. Now, simultaneously, there was a study done at the University of Virginia where they said, let's see how well people can identify human-human touch. So imagine this first scenario that I described where we were collecting data, where there's somebody, you and your partner sitting there touching each other, but now imagine there's no audio prompts. You're just being touched by the partner. How well can you identify what they're trying to communicate to you if you have these 6 scenarios? And you can see, same thing, attention, pretty easy. But as you're going down, not quite as good. But the key thing that I want to point out is that our overall accuracy, and we did do more analysis of each of the individual things, although 45% doesn't sound particularly good, human-human ability is only 57%. And when we did what's called a row-wise Radisharja coefficient analysis, we actually found that our results with the human-machine interaction and the human-human interaction scenario, there was no significant difference between them. So our system's basically able to perform as well as human-human scenario, which is pretty cool. Now, again, this performance in both sides is not particularly good, right? What could make these things better? Contextual grounding. So it's very uncommon that you're going to sit and there's going to be no context whatsoever, no understanding of the environment, no conversation with a partner. Somebody's just going to reach out to you and express something that's very, very uncommon in the real world. But we wanted to see how does adding contextual grounding basically change the way that people can interpret our systems here. So what we have here is, again, these 6 scenarios. We have people using our device. In this case, we actually used the roller device, also the one with the motors. And we basically said, how does adding context basically change the way that people perceive these cues? And so we do this on what's called a valence and arousal scale. So these are metrics that are connected with sort of the emotional side. And so here we can see that the valence and arousal, basically the having context enabled, we have a significant difference in the majority of these systems. So calming is one that doesn't quite change the arousal, but does change the valence. So again, this is 2 things that are connected sort of with the emotional connection. And then the same thing, if we look at the difference between our 2 devices here, how does it change the valence and arousal? And we see that basically we're able to change the arousal between the 2 devices, but not necessarily the valence. So again, depending on what system you use, you might want to use one or the other. Okay, so now I'll move to sort of the last part of my talk here, which is just talking, again, how do we go from now just the forearm to larger areas of the body? And so here's when I started to work more in developing these soft haptic actuators. So again, these things that are very new. And I showed this before here, that this is one of the earlier stages of these soft actuators, again, made of this LDPE tubing that can be sort of heat sealed into different shapes. So this is sort of an example here. I said, well, what if I took these and I actually embedded them into a vest? So again, something that's larger on the body. Could I take advantage of all the skin space, or skin real estate on the back, so we can do additional types of feedback? And so we said, okay, well, we could just add these pouches sort of laid flat like this. You can inflate them. Maybe we could add different designs into them. But there's challenges with this, that it takes a lot of time to inflate. If you want things to have this large contact area, which is what you'd be able to get from these pouches here, you need big bags, which again is going to change the dynamics of it. So we decided to take some inspiration from macro mini robotic actuation, which is basically to have like multiple manipulators in series. And we said, what if we stacked these pouches on top of each other so we could control them individually and improve the dynamics of the system? So we basically then stacked these and put these on the vest as well. But we wanted to see, again, how well does this work in the scale of haptics, and does this help with fitting people of different shapes and sizes, right? Like, are we only going to see improvement if something's already tightly fit, or vice versa? So we basically took this and we designed, this is a very messy classic lab photo, where we've got lots of different tubes coming out. Again, we want to try to minimize the number of these, but we can see there's a little bit of curve in here based on how we place things such that it would sort of tightly wrap around your waist. So again, I use this actually in a lot of grant proposals to talk about different ideas of why we need to continue development in these areas, because this is a lot of components. So again, although this is a wearable system, clearly there are very many things that keep you tethered to the real world. But for every pouch that exists here, there is a valve that allows you to open and close it. It allows air to flow in and then vacuum to pull air out. So we have a sort of control system that enables which ones are opening and closing, how much pressure we're allowing to go into each of these pouches, whether they're getting air vacuum, the timing of all of that. And so you can see we can control an individual pouch here, again, one that is inflating and deflating. Or maybe it's not deflating in that video, so I don't know it is. Or we can control multiple at the same time. So we've got 3 that are kind of inflating and deflating there. So again, we're going to conduct multiple studies. In this case, we first just want to see, can they actually feel a sensation that's being relayed, yes or no? And we're looking at this for the 2 different systems that we built, one with just that single layer of pouches and one with the stacked pouches. And what we see here is, this is a psychophysical method called staircase method, something that we use to collect the data, where basically we keep increasing a value until someone feels it, and we drop it back down until they can't. Then when they say they can't, we switch it so that it increases again until they can, and we go back and forth until we settle on a point and we can take an average. And the key here is that our single layer system, we have to increase the pressure really, really high in order for the individual to feel anything. So it takes a long time for you to actually feel any type of sensation from the system, versus our macro mini, we can actually use less pressure and they can feel it kind of right away. So that's sort of the key here, is that we actually have better control when we use this stacked approach than a single pouch. And again, if we look at this across multiple locations, we can see that there's some very large differences for some pouches, and then there's no real difference for other pouches. And part of this is based on the location that these pouches are located on the body. So if we look here at pouch 1, it's kind of close towards the shoulder. There's not a lot of room typically when you put on a shirt. It often sits on your shoulder, so there's maybe not so much of a difference between a single pouch or a stacked one. Versus kind of in the middle of your back here, pouches 5 and 9. The different curvature that people have, having stacked pouches might make things a little bit easier. And then same thing kind of here, pouch 14 here at the hips, oftentimes, our shirts and our clothes, they fit pretty snugly there. So we can kind of see, depending on where you're at the body, you might want to use some configurations over others. We also conducted a second study, and the video here is kind of important because it shows that basically when they feel a signal, this pops up here and they're asked to draw on this person wearing a vest where they felt the sensation that was relayed and basically how big it felt. What did it actually feel like on their back? And so they go and they keep going through to identify different things. So we change the different pressures that are relayed, the different pouches that are used, and then we collect all this data and we're able to create these heat maps that basically show what people perceived they felt on their back. And so on the top here, we have our single pouch system, and on the bottom here, we have our stacked pouch system. So in the blue here, you can see that these are pretty light, so not very many people sort of identified feeling things there. This kind of up here in the corner was a question mark, so if they didn't feel anything at all, they would just indicate there. So we can see that for these low pressures, they're not really feeling very much. As we increase the pressure, they're starting to feel more things, and they can kind of get the general area, but it's pretty small. Versus if we have our stack pouches here, there still are some scenarios where they can't quite feel it, but we're really getting these dark circles right off the bat, and they're pretty clustered. So this is just an example, but if we look at all of the data, we sort of find these same things hold true, that there's a difference between the two devices in the mean and standard deviation of these areas, and specifically that the contact area increases as the pressure increases, so just overarchingly between the systems, or for both of the systems. But then between the systems, the individuals are easier to identify the location with that macro mini system, so they have less instances in general where they're not feeling things and they find the actual location better. And then overarchingly again, they can just feel things better, there's less instances of no perception. So I'll try to wrap up here because I know we're basically at the end. That essentially we conducted another study to get their open response, where they really are saying it feels like a nice form-fitting suit. So again, something that we want to make sure that it fits well and is rolling sensations well. In general, people liked having the tighter fit of the stack pouches, that it, again, felt natural and like human touch. So again, something that we're going for. And with that, we then said, okay, our inspiration for this was actually to connect this with social touch here. Can we use our system to relay a data-driven human hug? So basically, we take our same pressure sleeve, we have someone wear it, collect data of what a human hug would be, and then we map those signals to our vest prototype and see, can we get the same output, so the same timing response. And this plot here is showing that we do okay. So we are able to get the same general pressures, so we're outputting the same pressures in the same locations, but the timing of these are not quite as good. So we may need to continue to customize sort of the stacking or the sizes of these pouches such that we get a better dynamic response. So basically, as you can imagine, human touches are really dynamic. We have really good control. These systems, we still need to work on this. Okay, so still ongoing in future work. This is great, we're able to build these systems, we're able to pre-program them to do things, but we want this to be something that happens in the real world. So can we have a sensing system that in real time is mapping these to these actuation-based systems that are built? And can we potentially use these, cross-country? Could we use our systems for touch therapy? So, these types of social cues also help people with anxiety or autism. And so could we find ways to understand when people are in these states and provide touch therapy for them? Could we also then continue to build on and embed different social touch gestures? We've also been working with Hunter Research Institute, who's been building a humanoid robot that can be teleoperated, and so embedding in our haptic feedback such that as you're controlling a robot in the real world, you're also able to get the feedback that the robot is interacting with them in the real world. So again, things that we're kind of working on in the same space. But there's also lots of other applications and ongoing projects within the lab. So again, we focus a lot on different things within system design, really working towards building different sensors and actuators and embedding them into various forms so that we can do different types of human-machine interaction. This is an example here of something for basically different types of surgery. So this is a needle insertion task for a haptic system connected to an ultrasound probe. But then also continuing to try to understand more and more about human haptic perception so we can better design the control systems and understand what we need for the sensors and actuators as well. And then I'd be remiss if I didn't advertise my graduate class, which I teach in the fall. So any of you who are still around, I teach MAE 6800, which is design and control of haptic systems. So we go through a lot of the theory, a lot of the modeling, we talk about different control schemes, we talk a lot about haptics within surgical systems and different applications. You do a bunch of different assignments, and part of those assignments is actually you build your own haptic system. So you start with this bag of parts here, you build this system, which we call HapKit, and then you actually do a bunch of different activities as a part of the class. to control that haptic. So here you see two haptics actually, one that is teleoperating the other, and vice versa. So this is bilateral teleoperation, and actually it's really small here, but there's a little virtual environment on the screen that you can connect your haptic to and control a virtual environment. So you're kind of working towards being able to design and build and control these different systems throughout the semester, such that you end with doing your own project that can really be connected to whatever application area you're excited about or interested in. So I had one group of students that was really excited about embedding or building a haptic toolkit that could be used for remote education, so learning chemistry. So they built a virtual environment and the hardware to basically teach students how to perform a titration, which was pretty cool. And then another project example here is a student who's really interested in sort of the aerospace industry and was previously a pilot. So they built basically a flight simulator, or that's not quite true. They embedded haptics within a flight simulator and built the hardware to be able to do that. So again, if you're around and you're interested, I teach this class in the fall. And then before I take questions, I just wanted to acknowledge all the many collaborators that I've had on these projects over the years, as well as the funding sources. So with that, take questions.
So maybe just one question, and then if you have more, Professor Nunez will be around. Anyone has one quick question?
Thank you for the presentation. And how do you see the private sector activities or progress in this research? Is it something just only for universities, or you can see some competitors in this price?
Yeah, so the question for anyone who's on Zoom was basically what's the activity in the private sector in this area, and is this really exclusively research that's done at the university level? So you could maybe see from my previous slide that we have funding coming from places that are not typical academic areas. So there's definitely a lot of interest within haptics in the private sector. Honda Research Institute, Toyota Research Institute, even not the Research Institute parts, but the overarching companies are doing a lot of work within haptics. Actually, for a long time, Sony has been doing a lot of work within haptics and are continuing to do so. A very large group that's interested in the haptics field here at the time when we had funding from them, they were Facebook. Obviously now they are Meta, and with the creation of Meta Reality Labs, they're obviously very, very interested in haptics. But then also, if, again, you're thinking of just your smartphones, there are haptic platforms in there. I have lots of friends who are haptic engineers at Apple, at Google, at some of these larger tech companies. Yeah, you'd be surprised how many companies are really interested in it and actually have positions in industry. I know Boeing, and I'm trying to think a couple other, Intuitive Surgical, people that are interested in medical robotics. Yeah, there's a lot of interest.
All right, thank you, Professor.